Hi everyone. Hey, today's lesson was all about polarity and whether molecules have the quality of being polar or non-polar. And before we started that discussion, we also had to talk about a quantity called electronegativity, which you came across last year. Uh, And the definition of that is in your workbooks. I think it's on page 18. But it is basically a measure of an atom's affinity for a bonded pair of electrons. So that's the definition that I remember. Affinity meaning a desire, an attraction to. So that's the definition, yeah, that I tend to think of. So it's a measure of an atom's affinity for a bonded pair of electrons, the attraction that it has. And there are a few factors that we have already discussed that affect that. Things like nuclear charge affects the magnitude of electronegativity. As the nuclear charge increases, so does the attraction for electrons, and including bonded electrons. But as the distance increases between valence electrons and bonded valence electrons, that attraction decreases, and same when you increase the amount of shielding. So as there's more energy levels between the valence electrons and the nucleus, the attraction decreases, the electrostatic attraction. So electronegativity also decreases. So with all that in mind, you will notice on page 18 that the trends follow the same sort of trends as some of the others we've seen, like atomic radii and so on. Anyway, to apply that to a molecule like hydrogen, we know that hydrogen has two electrons holding it together in a chemical bond. Because both of those atoms are identical, they both have the same value of electronegativity, and that is, I think, 2.1. So both have an electronegativity value of 2.1. All right, that kind of means that they both have the same attraction or affinity for those bonded electrons. And if you were drawing a cloud around hydrogen, you might draw it perfectly evenly around the whole molecule, showing that the electrons are spending the same amount of time around both atoms. And so the electrons are absolutely shared evenly. That's different when you have an atom that has a different electronegativity. So there I've kind of gone to the other end of the extreme, and I've put hydrogen with the atom that has the single largest electronegativity value, and so that's fluorine. And the effect of that is that those bonded electrons will spend more time around fluorine. Oops, more time, that should say, uh, around fluorine than hydrogen. If you were looking at the cloud of electrons, it might look more like sort of this kind of shape now. So they're spending less of the time around hydrogen and more of the time around fluorine. And so that's kind of distorted where those electrons are hanging out. And because they're spending more time around fluorine, at any point in time, fluorine is likely to have more electrons around it than it does protons. If it has both of those bonded electrons around it, then it will be negative because it has one more electron than proton. It doesn't happen all the time, so we call that a partial negative charge and a partial positive charge. Not fully negative or fully positive, but for a lot of the time, fluorine will have an extra electron around it, making it partially negative, and hydrogen partially positive. So that's the concept of electronegativity, and also the concept of polarity, because at that point in time, if you have a partial negative and a partial positive, we have what's called a bond dipole. Di meaning two, and pole meaning pole. So it means that it has in the bond two poles. So that hydrogen fluoride bond has a bond dipole. That is slightly negative, that is slightly positive. So a bit like poles on a magnet, it has a slightly negative and a slightly positive end. So that is called a polar bond, right? So that's cool. Then we moved on to what that means for bigger molecules. And so there are two things. For a molecule to be polar, it requires two conditions to be satisfied. Number one, it has to have polar bonds, right? Got to have those. And the second is it's got to have an asymmetrical shape. And I will demonstrate what that means. So let's have a look at this molecule here. Let's have a look at carbon dioxide. Okay, carbon dioxide has different atoms involved. Oxygen is is one of the most electronegative atoms, and carbon sort of sits there at about 2.5. So what it means is carbon has a lower electronegativity than oxygen. So the bonds within, sorry, the electrons within those bonds will be spending more time around oxygen than carbon. So I suppose if we were drawing a picture that showed those electrons, they might be looking more like something like this. So they're spending a lot of time around oxygen and less time around carbon, something like that. All right. So that means those bonds are polar. So it has the first quantity or quality of a polar molecule. It has polar bonds. But if we imagine those a bit like vectors in physics or like a tug of war, those bonds or that pull from oxygen is going in opposite directions on both sides of the molecule. So they cancel each other out. And that means that it is a non-polar molecule, even though it has polar bonds. Overall, that molecule is non-polar because those polar bonds cancel each other out, a bit like a tug of war. And that shape is nice and linear. That is a symmetrical shape. And so symmetrical shapes tend to result in this cancelling out of the polar bonds. And that is no good if you want to be a polar molecule. So even though carbon dioxide has polar bonds, it has a symmetrical shape. So those polar bonds cancel, and overall the molecule is non-polar. So moving along, let's have a look at one that's reasonably common, and we talked about how important it is. Water has also got polar bonds, but it's in a bent shape because of those lone electrons up there. If it didn't have those, it would be linear and life would be very different on Earth. However, at the moment, that's what we got. So oxygen is electronegative, hydrogen electropositive, and or slightly negative, slightly positive. And then we're looking at the shape. So it's got polar bonds. These are certainly polar bonds. That's great. If we look at how they're going, the electrons are attracted to oxygen a little bit, leaving hydrogen a little bit positive. Those, if you're talking about vectors, don't cancel now. And why don't they cancel? Well, we would say that water has an asymmetrical, a not very symmetrical shape. Yeah. And so overall, that is a polar molecule, right? So that's cool. Looking further on, and the last one here, maybe something like this, a little trickier. Sulfur hexafluoride, a bigger molecule, expanded octet, octahedral shape. Yeah, and in terms of shape, you've got these ones going up, you've got these four going around the equator there like that. All right, each of those bonds is polar. Fluorine we know is a really electronegative element, sulfur not so much. And so that's a polar bond. You've got 6 polar bonds there. So that's cool. However, if you look in space, And imagine that like a giant tug of war. Because that shape is symmetrical, uh, all of those bonds, polar bonds, will cancel out. So even though it has polar bonds, it is a non-polar molecule. Okay, and that's probably, well, I can't even spell it, molecule. That's probably enough for polarity. Take care out there, and we'll see you soon.